Grade 10 Chemistry, Advanced 3. In this lesson, we will be focusing on molecular shapes under Unit 4 Covalent Bonding. At the end of the lesson, you are expected to define and understand VSEPR bonding theory, understand hybridization and how it occurs, explain how to apply VSEPR model to predict molecular shapes, bond angle, and hybridization of a molecule. As you go through this lesson, it is very important for you to look at the following words: VSEPR model, bond angle, hybridization. Two lone pairs of electrons unshared will repel each other more than one lone pair of electrons repel a bonding pair of electrons. Repulsion is the least between two bonding pairs of electrons. As a result of the extra repulsion, the bond angles tend to slightly less as the bonds are squeezed together. VSEPR. V stands for valence, S for shell, E for electron, P for pair, and R for repulsion theory. The VSEPR is based on an arrangement that minimizes the repulsion of shared and unshared pairs of around the central atoms. Bonds are closer together, so repulsive forces are greater, and bonds are further apart, the repulsive forces are less. So all bonds are equally spaced out as far apart as possible. There are ways in predicting the shapes of molecules and ions. 1. Draw the dot and cross diagram or the Lewis structure to identify the number of lone pairs of electrons. 2. Count the number of sigma bond pairs or the single bond on the central atom. 3. Count the number of lone pairs on the central atom. And then this number of lone pairs is equal to the group number minus number of electrons used for bonding divided by 2. Step 4. Adding these two together, this defines the arrangement of the electron pairs. 5. The name of the shape depends on the position of the atoms around the central atom. For convenience, it is better to treat the double bond as a single bond. We will be analyzing the molecular shapes of the different compounds. We will be identifying its number of shared pairs or bonded pairs, lone pairs, hybrid orbitals, and the reason why it has its molecular shapes and also its band angles. For linear, we have a very good example of beryllium chloride. It's a molecule contains two pairs of electrons shared with central beryllium atom. These bonding electrons have a maximum separation, a bond angle of 180 degrees, and it is called to be the molecular shape is linear. Its hybrid orbitals is S and P. It has no lone pairs, and it has two bonded pairs. For trigonal planar, a very good example is aluminum trichloride. The three bonding electron pairs of aluminum trichloride have a maximum separation in the trigonal planar shape with 120 degrees band angles. It has an sp2 hybrid orbitals, 0 lone pairs, and 3 bonded pairs. For tetrahedral, we have a very good example of methane, or CH4. When the central atom in a molecule has 4 pairs of bonding electron, as CH4 does, the shape is tetrahedral. The band angles is 109.5 degrees, and it has an sp3 orbitals, no lone pairs or 0 lone pairs, and 4 shared pairs. And for trigonal pyramidal, NH3 ammonia is a very good example. It has 3 single covalent bonds and 1 lone pair. The lone pair takes up a greater amount of space than the shared pairs. There is a stronger repulsion between the lone pair and the bonding pairs than between two bonding pairs. The resulting geometry of trigonal pyramidal with 107.3 degrees bond angles. The hybrid orbitals of trigonal pyramidal is sp3. It has 1 lone pairs and 3 bonded pairs. In total, they have 4 pairs. And we have bent. A very good example of bent molecule is water. Water has 2 covalent bonds and 2 lone pairs. Repulsion between lone pairs causes the angle to be 104.5 degrees less than both tetrahedral and trigonal pyramidal. As a result, water molecules have a bent shape. It has a hybrid orbitals of sp3, 2 lone pairs, and 2 bonded pairs. In total, we have 4. And trigonal bipyramidal. A very good example is niobium pentabromide, in which it is a molecule that has 5 pairs of bonding electrons. The trigonal bipyramidal shape minimizes the repulsion of these shared electron pairs. A very good example of its hybrid orbitals are sp3d. It has 0 lone pairs, it has 5 bonded pairs, and total it has a total of 5 pairs. In octahedral, we have a very good example of sulfur hexafluoride and has no unshared pairs of electrons in the central atom. However, 6 shared pairs arranged about the central atom results in an octahedral shapes. Its band angle is 90 degrees, and then it has an hybrid orbitals of sp3d2, lone pairs of 0, shared pairs or bonded pairs of 6. Let us try to analyze the xenon tetrafluoride. This is the Lewis diagram of the xenon tetrafluoride. It has an 8 electrons to pair up with fluorine, needs 1 electron to complete octet. 4 covalent bonds are formed in order to have a complete octet. So there were 4 bonded pairs and 2 lone pairs. So therefore, as the result of the total number of electron pair is 6, the shape is based on an octahedron. There are 2 possible spatial arrangements of the lone pairs. The preferred shape of these 2 lone pairs opposite each other as far as right possible because the lone pairs repel more than bonding pairs. So the band angle should be 90 degrees and the shape is square planar. We have this Lewis diagram. That's all. Thank you so much. I hope you learned something for today. Thank you once again and goodbye.